No, we are not sharing screen. Can you go back to doing share?
Cheers.
This is
The desktop.
okay. Can you flip to the next page real quick? Looks good, thank you.
Yep. And do any of these, right?
This one should,
This one.
that's wrong.
But there's also the discussion section.
Yeah.
Bad, I miss it. Good morning, man.
Hey, welcome back. I hope you all had a relaxing weekend. It seems everybody found their way to New York and back. You had lucky you had good weather for it. So, and I saw the pictures. It looked like it was a lot of fun. So anyway, we'll go ahead and get back and start with the collection. First one for the week is Cheng is going to tell us about heavy ions and jets. So good to have you. Thank you.
Great. Can people in the back hear me? Or I need microphone? No. Okay, great. Okay, so let's get started. So I'll be talking about heavy ions and jets. And it's probably a little bit different from what you heard last week, because this is kind of the sister field to EIC physics, but it's closely related. Okay, so the goals. So there are two things I'm gonna cover for these 2 days. So for the goal for today and tomorrow, first, I'm going to talk about heavy ion physics, like what it is, why do we study it, how is it relevant to EIC, and then how do we study it, like a few general ways people study heavy ion physics. And then the second half will be on jets. This will be probably tomorrow. First, I'll go over how jets look like how do they develop in vacuum? Like if you have a high energy quark, how do they become the jets? Like I'll give the roadmap. And then some application of jets, like what things have people been doing using jets to study? Okay, so that's the roadmap for these 2 days. So for today, let's start with heavy ions. Okay, so yeah, so this is what I mentioned already. So to talk about heavy ions, we should start from the basics. So let's go back all the way to the beginning and talk about the strong force and the quark-gluon plasma. And here are all the particles that in the Standard Model that we know, that you're probably familiar with. So we have the quarks, we have the leptons, neutrinos, and so on. And these are the matters, the part that made up our universe. And then we also have the force carriers. So we have the gluons, the photon Z and W bosons. And finally, like 10-ish years ago, we also found another one, which is the Higgs boson. Okay. And when we talk about the strength of these forces, about these four, then the strong force is much larger than other three. Right? So it's much larger than electromagnetic force, which is in turn larger than the weak force. There's also gravity, but it's too weak, so it's not in the scope of today's discussion. Okay, so we will be mostly focusing on the strong force today. Okay, and the strong force is theorized as QCD, as we know, and it's a highly successful theory, and it may be difficult, but it's very successful. And one of the features of the QCD theory is that there's something called atomic freedom and confinement, meaning that all the quarks and gluons, the basic players of the field, are never found alone. So they are always constrained in hadrons, in mesons or in baryons. Okay, and this is a fundamental property of the QCD. Like in normal temperatures, this is always the case. And it's also very important, even though may seem like in everyday life we don't feel it. Because if you look at the mass of everyday objects, actually most of them are from the strong force. Yeah. So in the news, you might see that people say the Higgs field is responsible for mass. That's just a small portion. And in everyday objects, it's actually the storm force that's made up of the mass. Okay. So this is all good. Now that we have this theory, let's try to push the boundary to see if we can push it into some interesting places. Okay, so for example, this is the QCD phase diagram, a cartoon of it. So we have temperature on one side and the density on the other side. Then on this phase diagram, we can put, for example, the nucleus will be somewhere down here. It's low temperature and some density. And neutron star will be all the way to the right. It's very dense and hottish. And now the question is that what happens in this big space here? So in this space, essentially is if we heat things up a lot and we compress things a lot, well, what will happen? And something interesting happens is that in that phase, the quarks and gluons can move outside the boundary of the nucleus. So what happens is that when it's, so if you think of the nucleus as kind of the wave packet, it's an oversimplification, but we can think of it this way. When the heat things up, the wave packets become larger. And when we compress it, they start to overlap. And when they start to overlap, things can jump across the sides. Right? So we can imagine that when we do this to the extreme, then we have a volume that things can move around without constraining to a single hadron. And that phase is what we call the quark-gluon plasma. Okay, so it's a plasma where quarks can go around, and there's no single hadron in there that things are constrained in. And this is also stated matter about microseconds after the Big Bang. So after the Big Bang, in the Big Bang picture, in the beginning, it's very dense and hot. And it's believed that about microseconds after that, this is the phase the universe is in, which makes this interesting to study. Okay, so now the question becomes, can we recreate this in lab to study them? Okay, and the answer is obviously yes, otherwise I won't be here. I'll be talking about something else. And the way to do that in a lab setting is to look at heavy ion collisions. Okay, so we have accelerate the heavy ions like lead ion, gold, xenon, and so on. You take your pick. And we accelerate to very high speed and collide them with each other. Okay, and in the top energy and in LHC and rich, we've been accelerating to the Lorentz gamma factor to about 2,700. So something of this order. And this is really, really big. So imagine if we zoom in to look at the nucleus to the size of basketball, then at this speed, it will be Lorentz constructed and it will be a thickness of a paper. So that is how high the energy is. The Lorentz construction makes this into this thick. Yeah, so we will have two kind of thin papers hitting each other at very high speed, even though at rest it's roundish. Okay, and after collision, this is how it looks like. So this is a head-on collision. They hit right on top of each other. And this is one example collision, and each line is a charged particle. So we have huge amount of particles created. There are also neutral particles that's not shown here. So in reality, it's even more than this. Okay, so to describe what happens after collision, this is roughly the timeline. So in the beginning, we have two very thin pancakes hitting each other, or paper. I think it's hitting each other. And right after they hit each other, they pass through each other and then dumps a lot of energy into the field, the strong force field in the middle. Okay. And it's estimated they dump like 90% of energy. Really, most of the energy is dumped in there. And after the energy is dumped here, it's very dense and there's a lot of energy in there and it becomes very hot. And soon after that, the quark-gluon plasma is formed in the middle. Okay. And after this is formed, because this collision happens in vacuum, there's nothing to hold it in place. And it's a very hot object and very dense. So it starts to expand like crazy. And during the expansion, the temperature goes down, the energy also goes down. And eventually it decays and goes down into a bunch of particles, which then we detect. Okay, so what we want to study is the space, like what happens here when there's quark-gluon plasma. Okay, and the whole thing is very short-lived. So it's estimated it's about 10 to the minus 22, minus 23 seconds, or 10 femtometer over C, something of this order. Okay, so put the lifetime in context. If you draw the particle lifetime on the chart, we can see the decay time of all the common particles, and the quark-gluon plasma is here. So it's very short-lived, even compared to the many other particles. Okay, so here is the basic property of the quark-gluon plasma that's created. The lifetime is like 10 femtometer over C that we mentioned. The temperature turns out to be like 100 something to few hundred MeV over K. And in usual units, it's few trillion kelvins. Okay. And what we know is that it decays and cool down and converts to particles at around 160-ish, something around here of this ballpark. And the initial size is essentially the size of the nucleus. So it's like 10 femtometer. So this gives you an idea of how, like it's 10 femtometer, and after 10, order of 10 femtometer over C, it decays. And so yeah, that's roughly how it is. And so far, we see that it can be quite well described by the thermodynamics, which is kind of which is similar to the one used to describe a liquid. So it's kind of the hot quantum liquid. Okay, great. So we know now that we see that there is that phase, let's go back to the Fukuzzi phase diagram and lay things out. Okay. And as usual, we have the temperature and the baryon density here. We have the nucleus here, and we have some crazy things up there that I'm not going to talk about. That's hypothesized. Now, down here, we have hadrons. So when the temperature is not high or density is not big, we have the QCD, we see a bunch of hadrons floating around. And up here, we have QGP, quark-gluon plasma. Okay. So now the question one can ask is, how do they transition to each other? Yeah, because that's some fundamental property of the QCD. Imagine you're studying water, and this is equivalent to map out when ice becomes water. Like we want to know the boundary. Yeah. Okay, and so there are some guesses. So for example, close to zero net baryon density, it's believed that there is some crossover. So lattice calculations seem to indicate that it's probably a crossover. So there's no phase transition from one to other. It just smoothly goes through it, at least around here. And if there's a transition somewhere else, then there can be a critical point where transition happens here and not here, and so on. So this is what we want to map out. And we can use heavy ion collisions to help it. Okay, so for heavy ion collisions, well, after we collide, we trace out a line on here in terms of temperature and density. And if we map out the top energy collision at RIG and LHT, then they trace roughly these lines. So they go over the crossover region. So it's nice to study them, but it doesn't help with trying to find all these different things. Okay. And that's where the Rig beam energy scan comes into play. So by colliding at smaller energies, we can map out more different places on the QCD phase diagram. And that's why people, so for top energy, we can look at this region. And for lower energy, we can look at both regions. And that's why it's quite interesting to scan the full range of energy instead of just the highest energy, because we can probe different things with them. Okay, and another reason for studying heavy ion is that we can link back to the early universe. Because, for example, if this is the Big Bang picture, and so after the Big Bang, there's inflation, and then there's the QGP phase, quark-gluon plasma, about 1 microsecond, and then it decays a bunch of things, and eventually we reach the point of the cosmic microwave background, and then it evolves to today. And by using light and looking back on the sky, the farthest we can look is the TMB. And beyond this point, it's opaque to light, so we cannot study things that's beyond this using light. And heavy ion collision gives us another way to study things that's before that, so that we can kind of go from this way to there, and then astronomy and other things can go on that direction, and we try to meet in the middle. And one example of how this can manifest itself is that suppose from QGP to no QGP, there's a phase transition. Okay, so if the phase transition is like water to vapor, if you boil water, you get bubbles, right? And if there are bubbles formed, and the whole thing is rapidly expanding, then the bubbles will be kind of frozen in time. And this can give us some potential signature in the cosmic microwave background power stuff. But we will not see such a uniformity in the CMB. Okay, so this is one example of how things might connect. And if we go back to the QCD phase diagram and trace out where the early universe is, unfortunately, is this line, or fortunately. So it's in the region where we believe to have a crossover, which means that probably there's no big bubbles forming. And this is in line with what we see in the CMB. It's very uniform across the whole sky. So at least things are so consistent. Okay, cool. So that was the brief introduction of the field, what people are looking at, or some of the things, because time left out a lot of things, but this is some of the things people are looking at. So now let's make things a little bit more concrete. Okay, so how do we study the property of the quark-gluon plasma? So we have a plasma, we want to study a property of it. And there are generally two broad categories. So quark-gluon plasma decays. So we can study the decay product, see what it decays into. And we can study what happens if some things go through it and look at the interaction. Okay, and I'll give some examples of each of these classes. So let's look at the first class first, which is the decay products of the quark-gluon plasma. Okay. So the first thing is that we want to establish that it's like a liquid. And so we look for signatures that links to the liquidness of the quark-gluon plasma. And one of the things is that liquids can move as a whole. So there's a common velocity. Yeah. And if the particles are in it, you will get pushed by the liquid to go roughly in the same direction, same velocity. And we can try to look for a signature of this thing. And to do this, we can look at the spectra of, for example, ion. Here, the y-axis is randomly normalized, so we just look at the shape. Okay. So the blue line is the reference, is what the spectra of what we see in proton-proton collisions, where we believe that there's no quark-gluon plasma. The red line is lead-lead collisions where we believe there is a quark plasma. And we see some distortions. So things seem to be pushed a little bit. Things are a little bit harder. And we can also look at another heavier particles. So if the particles are pushed to have common speed, roughly, then heavier particles will have a larger momentum. So it will feel the effect. And indeed, we see a similar picture. So if we look at the proton, the green is what happens in reference without quantum plasma. And the yellow is with the quantum plasma. Okay, so we see that the distortion is more. So it's in line with the liquid interpretation of this. Okay, and another thing we can look for is the density and pressure gradient. Okay, so when they collide, so I'm not sure if you can see these are the two nucleus. If you look from the collision line, and this is the overlap area. Okay, and so this is the initial shape of the quark plasma that's produced if they don't collide head-on. And if this is a liquid, then it makes sense to talk about pressure. And the pressure force is roughly the pressure gradient, which means that if you have some pressure here, vacuum outside, then there will be some pressure gradient from the center to the side. And because this is shorter, so the pressure gradient will be larger in this direction than in these directions. So there will be more push by the liquid in the horizontal direction compared to the vertical direction. Okay, and the result of this is that if we look at particle production as a function of this angle, then we should see more particle in one direction and less particle in another direction. Okay, and that is exactly what we see in experiments. So this is the phi angle, which is around here. And we see more particles in some directions and less particles in other directions. Okay, and this signature is unique to the quantum plasma. That we see this kind of correlation across a very wide range in the detector. Okay, and so what can we learn from this kind of correlation? One thing is that we can look at the V2, which is this size of this modulation. And we compare different particles to see how they line up. And it turns out that this amount of modulation lines up quite nicely if we scale things by number of quarks. So if it's a meson, we have 2 valence quarks, then you have some modulation. If we have baryons, we have 3 valence quark, then you have larger variation. But if we scale by the number of quarks, everything seems to line up quite nicely. And this tells us that inside quantum plasma, the quarks probably are the thing that's flowing. And when you combine quarks into mesons or baryons later on, you naturally pick up smaller or larger modulation because you need 2 valence quarks or 3 valence quarks. Okay, so this is nice to see. Another thing we can look at is the viscosity. So for fluids, if you try to deform it, it will give you some resistance, and that's called viscosity. Okay, so for example, the shear viscosity is that if you have a slab of liquid, you try to move the top part in some velocity, you keep the bottom part the same, you will feel a force going up the other way direction. And that's the shear viscosity. The larger the viscosity is, the harder it is to move things. Okay, and how does that connect to the heavy ions? So remember, there's the pressure gradient. So there's more push in one direction and less push in other direction. But if the whole thing is very viscous, when they try to push things, the force will be smeared out to other directions. So the end product is that if this is like honey, then the modulation we see at the end should be smaller compared to if this is more like water. Okay, this is animation, which is PDF, so nothing here. Okay, and people have gone and tried to extract it. And here's one example. So they extracted the shear viscosity as a function of temperature. And the actual numbers it's not important for the moment. I would just want to know that it's quite small. Yeah, and it's almost, this tells us that the quark-gluon plasma behaves almost like a perfect liquid. So it flows very well, given the entropy that it has. Okay, and the other thing we can see is the strangeness enhancement. So this is another classical signature. So quark-gluon plasma is hot, and the temperature is larger than SS bar for some portion of it, or at least the same order. So strange quark is like 90 MeV, so it's 180 for SS bar. And when the temperature is that hot, then we can produce SS bar just by itself because it's hot. And the result is that if there is quark-gluon plasma, we expect more strange particles because they will be created inside the plasma. And this is what we see. So here is the ratio of number of particles compared to pion. Pion is just a reference, so it's not that important. What's important is that the smaller system, proton-proton and proton-ion collisions are all lie here, and ion-ion collisions are the points here. Okay. And we see clearly that things in ion-ion collisions is a little bit more compared to here. Okay, so this evidence is also in support of the kind of the quark-gluon plasma liquids interpretation. Yeah. If we look closer, then there are a lot to discuss here, but for now I'll leave it here and happy to discuss more afterward. Okay, so what do we know by analyzing the decay product? So we know that particles are pushed by the liquids. We know that it flows very well because the viscosity is quite small. And we see more strength are created. And there are also many other things that I don't mention, but these are the classic signatures that's attributed to quark-gluon plasma. And now let's move on to the other case. So what else can we study? Okay, so going one step further, let's think about how do we study the structure of things. And we follow basically the same script as what we always been doing. We shoot things at it and see what comes out. So one classic example is the Rutherford experiment, where we have gold foil, we shoot alpha particles, and then based on the distribution of the particles coming out, we know the structure of the atom. Right, so they conclude that there's a tight core and empty space, roughly. Okay, so this is one example from what we can learn by shooting things on things. Another example is, suppose we want to know the structure of the crystal, then we shoot X-ray, and then we've got diffraction patterns. Here's one example. Crystal, laser, we see diffraction pattern. And from the pattern, we can work back and learn something about the structure of the crystal. Okay, so we want to do the same thing for the quark-gluon plasma. And it turns out that we are in luck because when you collide things, sometimes one of them will have a violent collision and we will create high energy particles. And the end product is that the particle is created and then the quark-gluon plasma is created and then the particle flies through the quark-gluon plasma. So it's almost like a scattering experiment by itself, just by single collision. And all we have to do is pick out the cases where this happens. Okay, so now I'm going to give you a few examples of what we can learn from this to learn about the plasma. So first example is photons and leptons. Okay, so what do we see? So we can pick out the collisions where a high energy photon is created. Okay, so sometimes do a quick collision and we have photon jet, for example, or just photon plus something else. And then the photon can go to quark-gluon plasma and we can study it. And here we look at this quantity called RAA, which is essentially just the cross-section with quark-gluon plasma divided by cross-section without quark-gluon plasma. So we compare the hypothesis with quark-gluon plasma, that's the heavy ion collision, compare with the K hypothesis where there is no quark-gluon plasma from proton-proton collisions typically. And this ratio, if it's 1, it means that the cross-section is the same regardless of whether there's the plasma or not. And that means that it's not modified. If it's less than 1, it means that we see less coming out of quark-gluon plasma. If it's more than 1, we see more. Okay. And the result, we see everything is around 1, meaning that the cross-section for high energy photons is the same with or without the plasma. Okay. So this tells us that the plasma is roughly transparent to high energy photons, even though there's so high energy here, there, and density. Then we can also look at the electrons or muons. So for example, we look at Z boson, and it decays to electrons pairs or muon pairs. And the electron and muon pairs go through the plasma. So what do we see? We can compare the heavy ion data with what we expect from proton-proton collisions, which are the bands, and they are the same. So this tells us that also for electrons and muons, they pretty much just fly right through the quark-gluon plasma, at least the high energy ones. Okay. So even though the plasma is a ball of strong force and there's a lot happening there, if we have electromagnetic objects, they just go through it. It's almost transparent to it. Okay, so that's what we can learn. Now, another example is heavy quarks. By heavy quarks, I mean Trollman body. And the reason why heavy quarks is interesting is that the quark-gluon plasma temperature is not high enough to produce them. Okay. So when we see them, we know that it's produced at the beginning because in the free initial collision. And another thing is that the decay time is much larger than quark-gluon plasma lifetime. It's like millimeters or centimeters, which means that it stays as the heavy quark throughout the whole full QGP evolution. So it's kind of like a probe where we sample the whole thing, and then we see what the effect is. And we can use it to do many things. And yeah, I won't go into too much detail here, but I will just give you some examples of what I can learn. One thing that people look at is the quarkonia, which is QQ bar bound state. Okay, so in this case, for example, we have upsilon, and we have different states of the upsilon. So we have the upsilon 1 state, which is the most tightly bound. We have 2s, a little bit more loosely bound, 2s state. And then 3s is even more looser bound. Okay. And so all these have some binding energy. And when we submerge them into quark-gluon plasma, then what could happen is that, so there are a lot of quarks in the quark-gluon plasma. Right? And if the binding is loose, then the quark-gluon plasma can destroy it. Whereas when it's tight, then it's less likely to be destroyed. So by comparing what happens to these separately, we can probe the effect of having a system with different binding energy of how much is destroyed, how much is restored, and so on. Okay, and here's the suppression factor. So for example, what we see is that upsilon 1s is suppressed somehow. So like 2/3 are destroyed by the plasma. And when we go to a looser bound state, the 2s state, then almost 90% got destroyed. And the 3s is even more. Okay. So by doing this, we can kind of probe the temperature effect of quark-gluon plasma. So because it's hot, and if it's hot, if it's hotter, then it will destroy more. If it's colder, it will destroy less. And by this, we can learn something about that. Okay, and we can even flip the script and put something else into the Qualcomm Plasma to see what we can learn. Okay, and so this is using the same idea, except that we submerge in this case the X3872 particles in there. So this is a particle that's discovered like 20 years ago, roughly, and we don't know much about the structure of it. So it could be like the tetraquark state, or it could be like the DD-bound state. We don't really know yet. So by putting them into the Qualcomm Plasma and see how much get destroyed, we can learn a little bit more about whether it's more likely this or more likely this. Okay, so people went and measure, and it seems to have some estimate, even though the uncertainty is large. So we cannot say too much conclusive yet, but it's a nice direction. And with more data, I think we can shrink it and see where it ends. And that will tell us about the structure. Okay, another example of what we can learn from the interaction is the light quarks and gluons. In other words, the light jets. And this, stay tuned for tomorrow. This is the topic of tomorrow. Okay. So as a recap for the scattering part, so for the electroweak probes, so for the photons and leptons, these high energy ones, they just light right through, and they don't interact much. So the Qualcomm Plasma is transparent to electroweak force, essentially. And if we look at the heavy quarks, it's especially interesting because it's created at the beginning of collision and it samples the whole thing. And we can learn something about how it's modified. And there are also a lot more that we can learn from it. So I just wanted to give you some example of what we can learn. And of course, I'm happy to discuss more afterwards, of giving more examples. But this is just a taste of what people are doing in heavy ion physics. Okay. So I see I have like 15 minutes left. So let me go into the last subtopic, which is what happens when ions miss each other. Okay. So up to now, what we've been discussing is if we hit each other, we create Qualcomm Plasma, and that's interesting in study. Okay. And that's a large part of the heavy ion physics program. But there's also another part that's quite interesting, is to study when they miss each other, they don't hit each other. Okay, so what happens is that this is something that people call the ultra-peripheral collision. And the reason I'm spending some time on this part is because this is probably the closest, the part that's related to EIC the closest. Okay, and so this is the picture. So we have ion going one way, another ion going another way, but the impact parameters, so they don't touch each other. Okay. So in this case, we don't have hadronic collisions, but we can have electromagnetic interactions. Okay. And the reason for this is that the ions, in order to accelerate them, we have to strip out the electrons, so it's positively charged. And when you have a positively charged ion, we have electric fields stick out of it. And when we boost them into high velocity, then you can see the field lines start to get constructed on the side here. And these can be viewed as virtual photons that's just traveling together with the ion. So the closer you have, the more contracted and the higher energy virtual photon you have. And the farther you go, the lower energy it is. So the heavy ion collision is not just ion versus ion, it's ion plus a bunch of photon versus ion plus a bunch of photon. And the photons can also hit things. Okay, and the study of the ultra-peripheral collision, when they don't hit each other, essentially are the studies of how these EM fields interact with the other ion. So here's one example of the collision. In this case, we have ultrapropane collisions, and they create a muon pair and nothing else, because there's no hadronic collision, so things are very clean. We only see the extra things created. Okay, so one example is the J-side production. So in this case, we have a virtual photon coming in, hitting the ion or proton. You can have different targets and create a J-side. And this is the diagram. So it exchanges some gluons, homerons, and create a J-side. And this kind of diagram probably is more familiar to you because we're quite similar to what we do in EIC. And we can study different things. For example, if we look at the coherent scattering, in other words, when this doesn't break up. So in this case, we're just having a small notch, like the virtual photon gave us a small notch of the target. And typically there's a small momentum transfer, and this is sensitive to gluon PDF. So you can see there's gluon exchanges here. Okay, so that's the coherent case. How about the incoherent case? So sometimes the momentum transfer can be a bit large, and as a result, the target breaks up. Okay, so in this case, because the momentum transfer is typically slightly larger, you can look a little further into the nucleus on the target side. And it turns out that this is sensitive to sub-muon fluctuations. Okay. So depending on how the things fluctuate inside the nucleus, the result will be different. So as an example, here's H1 collaboration result. So this is technically not UPC, but it's similar things what we do. So the blue points are the incoherent results. So we see that as a function of momentum transfer, we have the cross section. Okay, and this is compared to two different theory predictions. So if we have a fluctuating proton, then the theory prediction is up here. And if it's a round proton, then the theory prediction is down here. So the incoherent scattering will have a very different result based on how the things are fluctuating inside the nucleus. And this is one way we can learn about the structure. Okay, coherent one, on the other hand, if things don't break up, doesn't change that much, which makes sense because we're just getting a little notch, and what happens in there is not that important. Okay, we can also look at exclusive digit production. So for example, we can have ion collision when they don't hit each other, but they interact so that we create a digit back to back. Okay, and this is the kind of diagram that produces that. So we have a photon coming in, hitting this, and then we create a QQ bar. Okay, and this is interesting because if we look at the two jets, sometimes they're not exactly back to back. And for this, we can form two things. For example, we can look at this, the difference, the PT, which is kind of the scale of the two parts, the momentum of the two parts. We can also add the momentum up, which is the QT, which is kind of the kick to the QQ bar system. Okay. And this kick is interesting because it can be sensitive to many things. So, for example, if there's a QQ bar system and it's kicked somehow, so that kick has to come from somewhere. Yeah, and there are many ways it can come. For example, if there's a mini jet somewhere that we don't see, that's possible. Or it can also come from initial state, from what's happening in the nucleus. And that allows some sensitivity to the transverse PDFs inside the nucleus. And people went and measure it. So here's the result from CMS. So for example, we have data here versus sub-Monte Carlo, and we see some difference. And I think it's still a little bit early to conclude anything too precise, but all we can say that is that they don't match. So something interesting is happening. Either this simulation doesn't capture everything, or there's something else. And yeah, we'll wait for further data to make this better to see what happens. Okay, so on top of this, we can also look at some interesting things that's not typically heavy ion physics. So for example, we can study photon-photon scattering. So when they don't hit each other, but the photons hit each other. Okay, so photons normally don't interact at tree level, but if you have higher order diagrams, you could have. And this is interesting study for many reasons. For example, first of all, it's a precision test of QED and QCD because this is loop diagram directly. Or we can also imagine there's some new physics in here, right? We can use this to search for new physics. If there are something else that couples to photon, then we should see a lot more. Yeah, and this is what people do using the result of this. This is one example to look for axion-like particles. So this is a new particle that couples to photon. And if we have this kind of diagram, we should see more of them. And then we compare the cross-section we see with the prediction, and we can exclude some hypotheses. And with this kind of measurement, you can see that it's exclude some portion of the phase space between like 10 to 100 GeV in mass for this particle. Okay, and we can also do some precision standard model studies. For example, we can look at G-2 for tau. And the idea here is that we have two photons coming in. We create a pair of taus. And then if there's the G-2 is not standard model, then the spectra will be modified, and we can study that. And people went and study it, and you can see that the uncertainty is quite nice. It's quite comparable to what lab has been doing. So this is nice. And but unfortunately, or fortunately, everything seems to be lined up with sun. So there's no new physics yet. But yeah, in the future, we will have more data and we see what happens here. Okay, so to wrap up for the heavy ion physics, first I want to say a few words on the synergy with EIC, which is why I'm talking about this here. So if we look at the heavy ion physics, at least from on the side of studying quark plasma, it's usually a combination of different effects. So we have cold nuclear effects. So from the how the nucleus look like, the PDFs, transverse PDFs, and all that. And then it's convoluted with the hot nuclear effect, which is something has to do with quark plasma. And measurements from EIC in the future can really constrain a lot of things in the cold nuclear phase part. So we will pin down the cold nuclear part very well. And in turn, we can understand the hot nuclear part well, because we have uncertainty reduced a lot right here. But also there's another direction, which is that for some cases like the ultra-peripheral collisions, there are also some capability for heavy ion physics to study the cold nuclear part. We have much less control. We don't have a polarized beam and so on, but it's a good basic version that we can compare things to. And I think by comparing both, we can advance the field forward. Okay, so yeah, so as I mentioned a few times, this is only a very small sampling of what's happening in heavy ion physics. And I'm happy to discuss more. Yeah, if you ask me some more topics, I can point you to things or I can describe things to you in the discussion session. And the study of heavy ion physics is essentially two parts. The first part is about the study of quark plasma, which is a phase of matter where protons are not confined in hadrons. It's very hot, very dense. And so far we see that it behaves like a hot quantum liquid. And we can study through many ways, for example, the decay products or through the interaction of things. And the other part is the ultra-peripheral collision, where the ions miss each other, but we still have a lot of interesting things going on that we can study. Okay. And there's a good synergy and connection with other fields, including the EIC physics that we'll mostly talk about in these 2 weeks. Okay, so that's all for today. Thank you.
Thank you. We have time for a couple of questions now. And remember, this evening at 7:30, we'll relax with snacks and drinks, and we can follow up with informal discussions. But if there are some questions now, we do have time for that. So
feel free to ask any questions. I went a little bit fast in the middle, so anything you don't understand. Yes.
So, when we think about the picture of the collision,
Mhm.
should we think of like center of mass frame or just lab frame?
So in the case of ion collision, it's the two frames are the same because
Yeah.
it's the same.
But some of them, like,
Yes.
just accelerate one beam, right?
Right.
Yeah.
Yeah, and usually both depending on the situation. For example, you have proton-lead collision, then some people usually think about the shifted frame, like the center mass frame, because the energy is different.
Okay.
Yeah, but
Yeah.
yeah.
Yeah, I ask this because I noticed there's slides about the gradient of dance.
Mhm.
And it's related to which direction has a stronger force or something.
Yes. So in theory, so what I mentioned was for theory experiments. In theory, when we talk about liquids,
Yeah.
it's always in the liquid frame. So it's,
Okay, so it should be like two spheres.
yeah, so you have liquid going, each part is going different direction. And when you want to calculate something, you go into the frame of that liquid locally and see what happens.
Nice. But I mean, so if we have like two spherical
Mhm.
shape, and if their center are not in line, like
Yep.
a little bit offline,
Yes.
then the overlap shape will be
Yes.
different. Like the longitudinal direction will be longer. So it's opposite to the figure that you show.
Yes. So in this case, the speed is so fast that
So
the
it
path,
should be sure.
yeah, the passover is almost instantaneous,
Okay,
unless you go down to few GeV collision, like very low energy collision,
okay.
but it's almost instantaneous. So it's almost like there's a shock and then things develop.
Okay, because your figure shows that there are two spherical things. This collision.
Yes. So that's if you look at from the collision side, one in paper, one out paper. Yeah, if you look from that direction, then the speed doesn't matter because
Okay.
yeah, it's inside and outside. You're looking at that direction.
Yeah,
In
this one.
right?
Yes, yes.
Yeah, here, one of them is going inside the board, one of them is going outside the board.
Okay, awesome.
Yeah,
This
so
one.
we look in that
Instead
direction.
of this.
Yeah.
The nature of QGP solid target experiments, like where the beam collides with the solid target.
You mean like the fixed target
Yeah,
experiment?
fixed target.
Yeah. So fixed targets, depending on if it's a block of target or the fixed target like in LHCb style. So in LHCb, it's one of the experiment in LHC. They have the option to put some gas into the interaction region. And when ion comes, it hits the gas almost at rest. So that in that case, it's equivalent to a lower energy heavy ion collision. Because if you go to the center of mass, the effective energy is lower. But otherwise, it's still roughly in vacuum. But if you have a block of material and things go into it, then things will be very different. And it's closer to a colorimeter. That's the next hour. Yeah. So it depends on what you mean here.
If there are no more questions, let's thank you, Chen, again, and let's go ahead, we'll break, we'll resume at 10:30. Thank you.
Mention that there's exotic states. D0 and D0R.